Next, we're going to talk about cyclic subgroups. We can always form a subgroup from any group G by taking an element of G and creating a set. So, for example, and let me write that down. We can always form a subgroup of any group G by taking an element of G say A and G, and creating the set. Let's say you have, maybe back here you have, say, negative a 0, or maybe the identity, I should call this. A star, A star, A star, A, etc. Or, if the operation is addition, these would just be plus signs here. And so, for example, let's consider Z8. Remember, that's going to be 1, 2, 3, 4, 5, 6, 7. And let's take an element from here. So make a cyclic subgroup. Using, say, 2. So let's take a look at that. And so what we want to do is we want to make up our group. And again, it'll have 2 in it. And then 2 plus 2. That's what was kind of indicated up here by the start. Whatever the operation is, you would keep doing it. So then another, say, 2 plus 2 plus 2. Then keep adding 2 plus 2 plus 2 plus 2. And now actually we better check before we go too far, see what we have. So here we have 2, we have 4, we have 6. And here we're going to have 8. But remember, with the groups Z8, this is mod 8. So 8's going to be 0. Now notice if we added another one, that would be 10 mod 8, which would be 2. If we added another, that'd be 12 mod 8, which is 4. So this is all we're going to get. In other words, it'll just keep repeating itself. And let me write this in order. So, and let me actually write this like this. So sometimes when they have a cyclic subgroup, they'll put like some kind of symbol like this to indicate it was generated by 2. And that gave us this group 0, 2, 4, 6, like this. And so this is the cyclic subgroup. generated by 2. And you could go through and prove that it's a group. It has an identity, and you go through and show that all the elements have inverses. If, for example, if you take, so the inverse of 6 would be 2, because if you take 6 plus 2, that would give you 8, but 8 mod 8 is 0. Now the inverse of 4 would be 4, because if you take 4 plus 4, you get 8. And 8 mod 8 is 0. And you can go through and note that they all have inverses, etc. And of course they're closed. If you add any of these two together, you'll get something in the set. So, and again, you're always going to get a subgroup if you take a member of a group and do this to whatever the binary operation is. You just keep repeatedly applying it. Now, if we consider the integers, say z, and let's say, so generate, or maybe I should say, like before, find the cyclic subgroup, or something that might be stated this way. Find the cyclic subgroup. Generated by 3. And where addition is the group operation. And so let's take a look at this. Now, one thing to note, of course, Z is going to be all integers, positive and negative. And so we're going to have to like maybe make a little bit of room here. So let's say if you have to have like 3 plus 3 is 6. 3 plus 6 is 9, 12, 15, all the way through. And then you have to go 3 in the negative direction as well. All the way back to negative infinity. So this would be the cyclic subgroup generated by 3. And of course, in this case, it doesn't repeat. Now, so in general, cyclic subgroup, let's call it H of the group G, would look something like this. It would be H would be equal to, say, A to the N, such that N is a member of the integers, where A is in the group G. So in other words, if you want to generate a subgroup with a member of G called A of G, it would be repeatedly applying whatever the group operation is. Now in the cases we looked at so far, the group operation was just addition. But now if the binary operation it is addition, we can say H is equal to NA such that, remember the double dots mean such that N is an integer. And that's kind of what we had up above here. So if we want to, again, where A, of course, is in G. And so like this is what we had like in this previous example. We generated it with 3. A would be 3. And then we generated each term by taking members of the integer Z. So we took, say, in fact, if you look back, say this would be Z equal -2, or I should say N equal -2, N equal -1, N equals 0, N equal 1, N equal 2, N equal 3, etc. It'd be the same thing as our previous example, but of course, since it was a finite group, it's just going to repeat itself. So here we could have thought of this as generating this, like this one could have been thought of as being generated by N equals 0, N equal 1, N equal 2, N equal 3, but then it'll repeat itself, back to 0, 2, on and on, because we're doing mod 8. And also the negatives would be repeated by some of these. But if you have an infinite group, it would just go on and on and on like this. So again, we can see from these last two examples that a cyclic subgroup can be finite or it can be infinite. This one is just going on and on forever. So again, the cyclic subgroup may be finite or infinite. And if the group is finite, then there is some integer m such that am equals e. Remember where e is the identity. And now let's say that m is the smallest number that produces e, then we say that this cyclic subgroup is of order m. So let me write that down. If m is the smallest integer that produces e, then we say this cyclic subgroup is of order M. So again, in the last one example we did, let's say back here. So for example, we had the Z8 let's say this. So consider the subgroup generated by 4 this time. So again, you can think of producing it several different ways. You can think, so again, we're considering addition to be the group operation. And let's say plus is the binary operation. Then if you have then 4 would be n times 4, like this, where n is in the integers. So let's generate the group. Again, you could start at 0 if you wanted to, but since we're generating a 4, I usually like to start at 4 to kind of emphasize where we're starting. So a 1 element's 4, but then the next one will be 4 plus 4, or 2 times 4. However you want to write it. Let me write it 2 times 4 this time. You can write 4 plus 4. But notice then this is going to be 8, but 8 mod 8 is 0. So our group is just going to be the element 0, 4, or again, I like to put them in order, which is usually good practice. Then this is going to be the cyclic subgroup 4. So notice, to get back to the identity, we had to take 2 times 4. Gave us the identity, right? Because that gave us 8, which gave us 0. So the order the group is 2. So that's what we meant up here. That, because that's the smallest number. If we start with 4, the smallest number you could multiply 4 by, or the smallest number of times you could add 4 was 2 to get us back to the identity, because 2 times 4 is the identity. Or you could think of it as 4 plus 4, adding them twice gave us the identity. So the order of the group is 2. Now, of course, notice also that 4 times 4 would have given us 16. And 16 mod 8 is also 0. So that would have still obeyed this here, but but 4 was not the smallest multiple of 4 to give us the identity, but it was 2. Again, cyclic subgroups have that pattern. So cyclic subgroups that are finite have the pattern that they are cyclic. They go in cycles. So, if you have, let's say, a, say, to the 0 power, which is the identity, and let's say a to the first, excuse me, a to the first, a second, a to the third. Then at some point here, they're going to start repeating a to the fourth. So in the subgroups that we had, so from the previous examples, from Z8, we had the 2 generated the subgroup 0, 2, 4, 6. And again, that would look something like this. Again, wherever you want to start, let's say this is 2, 4, 6, and then we got back to 0, and it's just in a cycle. Like this. Or we had 4, we generated that a minute ago, that had 0 and 4. Once again, it's a cycle. 4 and 0. Just keeps going in a cycle. Again, like over here, if we would have gotten to 0, we add another 2, we still go back 2, 4, and it just keeps going round and round and round. Same thing over here. So cyclic subgroups do have that repeating pattern. And we have a theorem that says every cyclic subgroup is abelian. And so, like, this maybe is not a formal proof, but this seems logical. Because let's say, for example, say for any A and B in the subgroup, we have A, and let me, excuse me, let me make this, maybe call this B and C. Say for any B and C in the subgroup, for any B and C, in the subgroup generated by A. We have B is going to be equal to A to the N, and C is equal A to the M for some integers, N and M. Because remember, all the elements of the cyclic subgroup are generated by, repeatedly applying the binary operation, say it's going to be like A to the N for some number and some integer. Another element's going to be A to the M. And then, so if we do whatever a binary operation is, let's say if we take BC, and you can put a star in there if you want to indicate the operation, but I'll just do it like this. Say BC is going to be equal to, up here, A to the N, A to the M, which when we add the exponent, it's going to be N plus M. And so if we take CB, it's going to be A to the M, A to the N, add those exponents. Of course, we can commute addition, of course, and this is going to be AN plus M. They're the same. So any two elements will commute. And you can see why it is. It's basically because they're all generated by the same A for some A in the group. And then, so the bases are always going to be the same, so they commute. So all cyclic subgroups are abelian. Again, remember, abelian means all the members in the group commute under the binary operation. And one other interesting note is suppose an element A in G generates a cyclic subgroup. And again, we'll represent it the way we represented a minute ago, like this. Then the subgroup generated by this element is the smallest subgroup that contains A. So again, if you generate a subgroup with a particular element, that will be the smallest subgroup that contains A. Remember, of course, we're talking about subgroups, not subsets. You could get a smaller subset that contains A, but you could not get a smaller subgroup. You may get one the same size. There are other ones possibly the same size, but there's going to be none smaller, no subgroup smaller that contains A. So let's take a look at this problem. Find all the subgroups generated by the element of Z12 and draw a lattice. So see if you can do this. Let me actually get you started a little bit here. So Z12 is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's Z12. And so let's see if you can generate all the subgroups. So of course, let me write them down. All the cyclic subgroups. And I should have said, yeah, I guess when I say generated by the element, that implies cyclic subgroups. So let me just write these down. And so let's take a look at this. Let me just start you. Of course, the first one will be just 0, because if you keep adding 0 to 0, again, we're under mod 11 addition. Again, remember, or addition mod 11. Excuse me, mod 12. I was looking at this. So this is under addition mod 12. And so this is going to be 0. And let me do another one here. Maybe do 4. 4 is going to be, of course, it'll be 4 plus 4, which is 8, plus 4, which is 12. But 12 mod 12 is going to be 0. And so go ahead and see if you can do the rest of them. Go ahead and stop the video. See if you can do the rest of them. There'll be repeats. Some of these will be the same, but see if you can generate all these. So stop the video now and see if you can generate all these cyclic subgroups. Did you stop the video and make your cyclic subgroups? So if you did, notice if we take 1, we get 1 plus 1 is 2, 3, 4, 5, and we would generate the whole of Z12. So if we use 1, we would get the whole group Z12. You could write it out if you wanted to, like this, that'd be fine. Or you can just write Z12. Now for 2, we would get 2, and that'd be like 2 times 1, and then 2 times 2, which is 4. 2 times 3, which is 8. Excuse me. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. 2 times 6 is 12, but 12 mod 12 is going to be 0. So we get that. And you could put those in order if you to make it look nicer. So how about 3? We get 3 times 1 is 3. 3 times 2 is 6. Or you could think of it as 3 and then 3 plus 3. The next one is 3 plus 3 plus 3. 9. And then this one's going to be 12, but 12 mod 12 is 0. I'd already done that. And 5. So this is something interesting about 5. Okay, it's going to be 5, 10. But the next one will be 15. So 15 mod 12 is going to be 3. So now you could just continue with 20, 25, 30 and apply mod 12 to those. That'd be fine. Or now that we've turned this into 3, we can now add 5 to this one. So you can do it either way. So let me do it that way. Let's add 5 to this, which is going to be 8. Then I'll add 5 to this, which is going to be 13. But 13 mod 12 is 1. And then add 5 to that, it's going to be 6. Add 5, that's going to be 11. Add 5, that's going to be 16. But 16 mod 12 is 4. And 4 plus 5 is 9. 5 plus 9 is 14. But 14 mod 12 is 2. 2 plus 5 is 7. And 7 plus 5 is 12. And 12 mod 12 is back to 0. So as I mentioned, when you calculate these, so if you get to the point here where this is more than 11, and so then like here we got the 15. 15 mod 12 was 3. Then you can just work with 3 from then on. And then same thing over here when we had 5 plus 8 was 13. 13 mod 12 was 1. Then you could just work with that. Or again, if you wanted to start from the beginning, we had 5, 10, 15, 20, 25, 30, 35, and so on. And if you were to apply mod 12 to these, like for example, let me just pick one here. Let's say for 35 mod 12. So 12 goes into this twice to give us 24, and the remainder is 11. So you could have generated these upper ones by just continuing adding 5 to the original, or you could do it the way I did it and just apply the mod 12 and then add 5 to those. But notice what we have here, though. Again, you can put them in order to make it look nicer, but this is going to be all the numbers in our group. So this is going to end up being equal to Z12. So let's do the next one. 6. 6 plus 6 is 12, which is 0 mod 12. So you have this. And 7. 7 plus 7 is 14. 14 mod 12 is 2. 2 plus 7 is 9. 9 plus 7 is 16. Mod 12 is 4. Plus 7 is 11. 11 plus 7 is 18, which is 6 mod 12. 7 plus 6 is 13, which is 1 mod 12. 1 plus 7 is 8. And then 8 plus 7 is 15. 15 mod 12 is 3. plus 7 is 10. 7 plus 10 is 17. Which is going to be 5 mod 12. Then finally, 5 plus 7 is 0. So we're back to the game. Notice once again, we got all the elements in the set. So this is also Z12. And we got the whole group back. So again, 8 plus 8 is 16. 16 mod 12 is 4. 4 plus 8 is 12. And that's 0 mod 12. 9. 9 plus 9 is 18, which is 6 mod 12. 9 plus 6 is 15, which is 3 mod 12. 9 plus 3 is 12, which is 0 mod 12. We can stop there. Finally, let's see, we're up to 10. And 10 plus 10, 20, which is 8 mod 12. 8 plus 10 is 18, which is 6 mod 12. 6 plus 10 is 16, which is 4 mod 12. 4 plus 10 is 14, which is 2 mod 12. And 2 plus 10 is 12 mod 12, which is 0. Now we can go through 11. You'll find if you do 11, you'll end up getting the whole group back again. I'll just write it down real quickly, but you can, hopefully you found this when you stop the video. And this would be Z12 like this. Now, notice what we have. Actually, some of these numbers generated the whole set, didn't they? The whole original group. So 1 generated the whole group, 5, 7, 11. And so there's a rule for this. So where this comes from is this rule for any members of Zn. So let's say you have the group Zn. Any members of this group Zn that are relatively prime to this number n will generate the whole group. So if a number is relatively prime to n, it'll generate the whole group. And so in the case of Z12, if we find its factors are 2, 2, and 3, if we factor it down as much as possible. So any numbers that don't have any factors in common with 12, if they don't have a 2 in, if they don't have a 2 or a 3, then they're relatively prime to 12. And so, for example, if we look through the list here, let's see the ones that are not relatively prime. Of course, 2 is not relatively prime because there's a 2 in 2. And 3 is not relatively prime because there's a 3 in 3. 4 is not relatively prime because 4 factors 2 times 2. There's 2 and 2 here. 6 is not relatively prime because if you factor 6, you get 2 times 3. It has at least one factor in common, actually has 2. 8 factors to 2 times 2 times 2, so 2 is in common. 9 factors to 3 times 3, so they both have 3s. 10 factors to 2 times 5, so they both have a 2. So those numbers will not generate the whole group. but the ones that are relatively prime. Now, 1 is relatively prime to any number, so it's going to generate the whole group. And also 5, 7, and 11 are relatively prime to 12 because the only factors of 5 are 1 and 5, and 5's not there. Remember, if you have a factor of 1 in common, that doesn't count. It relatively prime to me, you have no other common factor except 1. Same thing with 7. Its factor just 7 and 1. 11, no common factors. So 5, 7, 11 are relatively prime to 12. Therefore, when we make the cyclic subgroup, they will generate the entire group. They'll generate all of Z12. Now, of course, if your N happen to be prime, then all the members, of course, will generate Zn because all the members will be relatively prime to that N because N is prime, so it doesn't have any factors that it could be in common with any other numbers. So then also notice something interesting is that some of these were the same. Like, for example, 4 and 8 were the same. 3 and 9 were the same. 2 and 10 were the same. Now, this gets a little bit more complicated. So why are 2 and 10 the same? So now notice that the 2 has 6 elements. So it has order 6. And so it will be then 2 will be relatively prime. Excuse me, will be the same as any group 2 times H like this, where H is relatively prime to 6. So in the case of, say, 10, 10 is equal to 2 times 5. And then 5 was relatively prime to the order, which was 6. So that's why those were the same. And note, 2 and 6 were not the same. Because 6 was equal to 2 times 3, and 3 is not relatively prime. To 6, since 6 is equal to 2 times 3, they have a common factor. And then you could go through some of the others. And you could say, for example, 3 and 9 were the same. And now 3, when we look back at our numbers here, 3 had order 4. And so anything of the form 3H again, where H is relatively prime, the 4 will be the same. And so, for example, 9 is equal to 3 times 3. And of course, this is relatively prime to 4. And then, so then that also explains, once again, 6 is of this form. Notice 6 is equal to 3 times 2. It's of the same form as 9, except 2 is not relatively prime to 4, which of course is 2 times 2. They have the common factor 2. So that's why 3 was not equal to 6. And you could, there's a couple others, I believe. 4 and 8, you can kind of go through the same argument and show that that's true, why that's true, why they're the same. And let's do a couple more things here. Now it says about the lattice, and all that means it just wants us to show, like, what are subgroups of the others. So again, at the top, we had 1. That generated the whole group. Again, that was equal to Z12. So what would be the subgroups of 1? Of course, that would be really anything, and we won't put them all in. We'll just put maybe a representative one in. So, of course, 2 is going to be a subset, and 3 is going to be a subset. And also, again, we won't put the duplicates in, like we won't put 10 in, etc. And then notice that 4 is a subset of 2. And then for 3, it looks like, what is it? 6 would be a subset of 3. Now, we won't put the duplicates, as I mentioned. For example, 4 was the same as 8. We won't list that. Then finally, 0, which only has one element, is a subset of all these. So here's the lattice. And that's kind of what they mean by the lattice. Again, I didn't put duplicates in.